Hi, got it. Hi, this is John Bush, and I'd like to present a talk today on the adjustments to the lower aquifer model, the Palouse Basin, Moscow, and Pullman area, Pullman Watershed in Moscow, Idaho. The slide you're looking at is a photograph from standing on the east end of Kamiak Butte, and you're looking across the Palouse Hills to the east up here to Twin Peaks in the southern Palouse Range. The familiar Palouse Hills in the foreground, made up of lush hills, and it's beneath those hills is where our Miocene aquifers are. Uh, a couple other things to note, the basalts and the sediments of the Miocene aquifers end just about here where my cursor is going across. Uh, that's where the slope changes. Uh, so I will be talking about the agricultural slopes, and that's this slope going up to the forested area up on the Palouse Range. So three areas I'll be talking about is the Miocene aquifers primarily, but also the agricultural slopes and the forested slopes. Uh, the talk is about adjustments to the lower aquifer model, but it'll be also will review some of the material that I previously presented in a lecture series that's now available on PBAC. But I will review some of the concepts, and for those who didn't watch those videos, and for those who need to be have some of the basics reminded. Uh, so let's sort of talk about where we're going to go. Before I want to do that, I'd like to thank Steve Robuchon of PBAC for helping me put the Zoom talk together, and for Pamela Dunlap for helping me put the slides together. So let's take a little look about what we're going to talk about. We'll make a couple of statements on why are we making adjustments. We're going to review assumptions and data. We're going to raise some questions about the model, about our present thinking. Uh, it boils down to what we're really interested, what most people are interested in, is the recharge, because we drink our water, we use our water, it's primarily coming from the lower aquifer. So where's the recharge coming from? How much is that recharge? So we're going to focus a little bit on the thinking that helps us review a little bit where our thinking has been. And then we'll make a quick summary at the end, because in my review of going over the model, we made some adjustments. So we'll talk about those adjustments, and then we'll come down and make a couple conclusions and suggestions. So let's see, get my thing organized here in my mind. So why do you make adjustments? I think sometimes we forget that there's never really a final answer. And models are meant to be questioned. They're a framework for thinking. Uh, so you have a model, you think about what you've learned, and you keep adding to that. And at some point, if your model needs adjusted, you adjust it. You make the adjustments as needed. All models, whether they're qualitative or quantitative, the word model means they're a framework for thinking. Now, at some point, if your model is not working, it's not calling the shots, it's not making any sense, and then you abandon the model and start over. So what I'm presenting here is sort of some adjustments to the present day thinking about our lower aquifer system, which is where we get most of our water from. So we're going to stick with adjusting the model. I think the model is good. It just needs some fine tuning. So we're going to talk about that. We'll talk a little bit about the model, and then we'll talk about why we're making those adjustments. So before starting, what are some of the assumptions? When we put all the data together, you got to remember there are hundreds of publications projects, reports, well reports on the aquifer system in the Moscow-Pullman area. And when you put the whole picture together in some kind of explanation or some kind of simplified explanation, there are some assumptions that you make. And we made tens of those, but I'm just listing the six major ones that I use. Now, remember, when I use the word I, it's really a summary of work going back over 100 years, going back to the first reports in the late 1800s, all the way up to the present day. So I might use the word I a lot. It's my summary of lots of work, lots of different backgrounds. One of the first assumptions is that the lower aquifer is interconnected over a large area. We know that it's very compartmentalized, but we have pumping wells in both Moscow and Pullman that are producing very large amounts of water, some of the largest in the Columbia River Plateau. But the water levels are consistent between all of our lower aquifers, meaning that it's interconnected over a large area, which we call the Palouse Basin. Another assumption that I'm making on my modeling and my thinking, is that there's significant moderate recharge. Some people still are cringing to the idea, hanging on to the idea that there's not significant moderate recharge. It's true that the recharge is less than what we're using, but there is a significant amount of moderate recharge. And that leads us to the fact that reported water dates that we had, the carbon-14 dates of the age of the water, are incorrect. It's not that the techniques and the research that was done to determine the dates was done poorly. It was just that the modeling was not quite correct. They had made a wrong assumption. They did good work, but the dates reported, particularly that the water is all Pleistocene age or 20,000 years old, is probably not correct, because there is significant recharge. Another assumption that I follow is that both the sediment and the basalt aquifers are important. So you might ask yourself, well, so what? Well, in the past, we tended to think in our modeling and our thinking that the water was primarily coming from basalt aquifers, and that's not correct. The water that we're drinking from the lower aquifer is coming from a combination of the sediments and the basalts. Another assumption is that if we have the correct data, if we have good well reports and access to good rock chips from the drilling operation, basalt flows, individual basalt flows, can be correlated from well to well. And that's extremely important. Whether the water is coming from the sediment or coming from the basalt, the correlation of flows from place to place help us identify the production zones and help us understand how the aquifer works. And we can now correlate most flows from Moscow to Pullman and throughout other areas of the Palouse Basin. And one last assumption that I have made when I tried to pull together a model, is that infiltration from the surface, I mean precipitation or influx from stream channels, it's very limited over much of the basin. This is another thing that down through the years we seem to forget. We've done a lot of studies. The data is a little confusing, but when you pull it all together, you realize that the water that we're drinking in our lower aquifer system is just not being supplied from direct infiltration from the surface over the Palouse Basin. And it's not being supplied from influx into streams. Okay, let's take a little look and reminder of what the subsurface geology looks like. I need to take a little swallow of water. My voice is already giving out a bit. This is a generalized cross-section, a very generalized cross-section. It's in several publications, several theses, several reports. It goes from the east in Moscow over to Pullman on the west. It's not the scale, but it does illustrate the the relationships of the rocks and the sediments and so forth. The yellow are the sediments. The blue up here is the basalt flow called the basalt of Lolo, belongs to the Wanapum Formation. It's the flow that you see, it's the basalt that you see outcropping in all the quarries and road cuts between Moscow and Pullman. And that flow blankets the entire basin. The green one here is the Grand Ronde flows. We have divided those Grand Ronde flows, and it may not be important to remember all those intervals. What's interesting is over in Pullman, this line here is about the WSU well number 7, which was a production well and a research well. That well showed that there's at least 2,200 feet of basalts and sediments below Pullman. And we generally refer to as the water coming from the Grand Ronde basalts, we refer to them as the lower aquifer. But if it's interesting, in Pullman, the primary water, the water that you're using, is coming from what we call the R2 interval, or if you think about it, just want to think about it, it's the upper part of the Grand Ronde. The test well showed that the aquifers below that level are not as prolific. With the exception of this well, which is getting water both from the upper and the lower part, all the main production in Pullman is coming from that interval. And when you go across to the east to Moscow, most of the water there is coming from the same interval, but it's also coming from the sediments. There are 3 wells which get water from the bottom also below that interval. So Moscow is a mixture of water coming from down against the basement rocks and water coming primarily from this, what we call the R2 interval. The general model that I've presented based on a lot of data is that water is being delivered to the basalts via the sediments. In this case, this is an east-west cross section. So you sort of got to think about looking into the cross section. So the model would say that the water is primarily coming down from the Palouse range into Moscow and into the sediments first. And then the water transfers itself into thin pinch out zones of the basalt and then moves into what we call intraflow zones and moves across the central part of the basin into Pullman, where we tap those intervals. Also in Pullman, one thing to point out is that surprisingly, the most prolific zone is a sediment zone at the base of the R2. When you look at the whole picture, the generalized story here, you can think about it as segment A, the east, segment B, the central area, and segment C, the western area. Segment A is dominated by sediments on the Idaho side. This line, this idealized line here, is about the boundary of the state boundary between Idaho and Washington. Segment B is this, what I call the central area, and out here, the salts dominate the sequence, and they are very horizontal. In other words, the contacts are not deformed, and you can trace them. You can look at the well logs and sometimes trace an individual basalt flow from one well to the other with very dense centers, what we call intraflow contacts. So the water is migrating, excuse me, from the east into those contacts and then over to the Pullman area. In the western part, the rocks are not horizontal. They're slightly folded. Hills, you could call them subsurface hills and valleys if you wish. We call it a syncline, like illustrated right here, or an anticline illustrated here. If you want to get a feel, they're not very big folds, but if you get a feel for that, you can think about being in downtown Pullman and driving up the hill towards Colfax, you end up going up the past the Hilltop Restaurant. And as you're driving up that hill, you're going up a slope on that subsurface anticline. So, okay, that's sort of a summary of the model. What we want to do now is, in my case, and always what you should always do, you should always use the model for thinking and raise questions and make some reality checks. So what I wanted to do, and I did this the last 2 or 3 months, I want to go back over what I presented in the previous lectures and ask some questions. It's hard to question some of your own thinking, but that's what you should do, and see what new things came up and does the model hold up. So sometimes we'll be starting and just talk about a segment and see how well the data, the information that I presented, the thinking that's out there, is it holding up? Does it make sense? So that's what we're going to do here. We're going to go across the basin. We'll start a little bit with the central part of the area. We can look at it here on segment B on the generalized diagram, or we can look at a little more complicated diagram. This diagram, again, this is a more detailed cross section. It starts again on the east where you see all these yellow sediments. And then the reds on here is where most of our water is coming from. This is what we call the R2 zone. You can see a little bit where the wells are located. The blue up here is that basalt of Lolo, which mantles the whole area. And then here's the deeper Grand Run from which we're not getting much water from. It's the same, it's a little more detailed. Those who want to look at even more detail, this cross section is illustrated both on PBAC webpage, and it's also illustrated on the Idaho Geological Survey's webpage. So if you want to look at more details, this is even a generalized drawing from the illustration that is presented on their pages. Now we're talking about the central part of the area. So we go out here and look at this central part. The flows are what we call relatively horizontal. They're not deformed. The biggest thing from this central area, the biggest piece of evidence, is this Lolo. There's just amazing amount of evidence that shows there's not any water getting through this top uppermost flow down into the lower aquifer system. We could even jump over into Moscow outside of the central area where we have what we call an upper aquifer. That is producing enough water for some municipal supplies. That same flow is prohibiting water from getting down into the upper aquifer, out into the main portions of the upper aquifer, and down into the lower aquifer. That forms a blanket over the central part of the area. So I thought about checking that because I keep making the point that there's not much vertical infiltration from either the streams or from vertical precipitation down through the loess, down through the basalt of Lolo, and down into the lower aquifer. The biggest thing, there's lots of reasons that shows that the water is not, significant water is not infiltrating from the surface. The biggest thing is this, the biggest impediment to the vertical infiltration is the Lolo flow. It averages about 165 feet to 175 feet in thickness. It has a very dense center. And when you go through the literature, and I went through some of it again, there are tens of articles, publications, projects, experiments, quantitative data, qualitative data. They all point to the same thing. In Columbia River basalts, in dense flows that are over 80 feet in thickness, the dense centers, particularly where they're not deformed, prohibited water from moving from the top to the bottom. From a driller's point of view, simply when you drill down through the Lolo, you can be below, you can hit some water in the top of the flow because the top has some fractures. You get to the center part, it's dense. Occasionally you get a little water, you just not much water getting through that. So again, what I'm doing here is trying to check the thinking about infiltration from the surface. The same central area, you can check all the data and information, and points up to the fact that, as Heinemann way back in '94 pointed out, Paradise Creek, once it leaves the Idaho boundary, is not influxing into the Grand Ronde. And there's drill log information, one after another, that shows that that's not happening. So this is sort of testing the one assumption that infiltration from the surface down into lower aquifers is not significant. Some people would point out, well, we have proof that there's an influx over here in Moscow. Well, that influx is getting into the top of the low low. It's not getting through the low low into the lower aquifers. So that's sort of a basic thinking. And I think the work on the central part of the area is standing up and holding its own. Now let's look a little bit out here to the western part of our lower aquifer system. And here I've ran into a couple walls showing we still don't have enough information. And let's talk about those and talk about maybe a small adjustment to the model or the information that I presented earlier. Once again, my voice seems to be crackling today, so I need to get a drink of water. The information I presented, and you can see it better on this diagram than you can on the more generalized one. The rocks as you get into Pullman are what we call folded. Here's this anticline or this subsurface hill. Here's a subsurface valley or syncline. This is right in downtown Pullman. The hill, the anticline, is on the edge of Pullman. And then if you follow the flows, they extend on out into what we call the Union Flat Creek area. So one piece of information that I double checked is correct. There's some observation wells out there, not shown on this diagram, out here in Union Flat Creek. There's some observation wells that tapped into the top of the Grand Ronde. And the water levels there are similar to those in the Moscow Pullman area, similar to the pumping centers here in Pullman. So that tells us that the Union Flat Creek area is connected to the other part of the basin. What it doesn't tell us, however, is that how is it connected? Does it have the same hydraulic conductivities that we have in Pullman, or doesn't it? You got to remember that up here in Pullman and Moscow, we'll just talk about Pullman for a minute. Those wells are exceptional for even in comparison around the Columbia River Basin, particularly in the northeastern part. They're exceptional. We pump a tremendous amount of water from those. And the same over in Moscow City 10, right on the state line, which is about there. That well has a capacity of close to 3,000 gallons a minute. These are exceptional wells. So you ask yourself, why? So come back here to the folded area, and my thinking, and some other people's thinking, that these folds are holding back the water from running out into the Union Flat Creek. Yeah, they're connected, but I don't think they're connected in a very good manner. It is unfortunate we don't have a production well out here in Union Flat Creek area. So I have to go, it's only based on geologic thinking that folds tend to slow down the water movement and redirect the water movement. If we project these folds into the subsurface to the north, it turns out they drop in elevation to the north, and folds and synclines and anticlines have been shown all over the Columbia River Basin to be impediments to water, to be barriers to water, or conduits for the water. In either case, they redirect the water movement. And what I'm saying in Pullman is that the water comes across the basin, encounters these folds, and then it causes the water to move to the northwest. So what I would add to ask myself is, are you sure these folds are here? And the reason I rechecked that information is there are still some people who don't want to believe that these folds are even present. So let's take a look at what data we have. This is a simple diagram for one published on PBank and one published with the Idaho Geological Survey. It's what we call a structural contour map on top of the Grand Ronde. You can think of it as a topographic map of that surface. So in other words, we have removed all the overlying material down to the top of the Grand Ronde. And when you look at this subtopographic map, you see that in Moscow, you got all these lines, the elevation of the surface drops a lot. This elevation is dropping a lot due to the fact that the flows are pinching out. So if you think about walking from, in those days, walking from on the top of that surface, it's a subsurface, walking on that surface, you would get to the central part of the area where there are horizontal basalt flows, and these wide contour lines are about 50 feet in elevation apart, in thickness apart. So you walk across the flat area, but when you get into Pullman, in order to get out to the west, you got to drop down into a valley and up over a hill before you get out into the Union Flat Creek area. So here's this hill. I call it an anticline. Geologists call it an anticline. Is it true that it's an anticline, or is it just a subsurface hill? Well, the data that I showed you on this map was rechecked. It was checked to information that we have good data from to the north and to the south, and it is in fact, rocks are dipping, sloping to the northwest towards what we call Smoot Hill, which is all quartzite, an impervious barrier to groundwater flow. Here's this hill. You can see this anticline dropping to the northwest. So the idea that I presented, it's strong geologic evidence, is that the water is moving across the basin, hits this fold, hits the syncline, and is redirecting the water to the northwest. We don't have, I have to admit, don't have a lot of hydrological data to support that. One of the reasons is since the water levels are consistent pretty much throughout the lower aquifer, you can't use water levels to show where the water is moving. Typically, if you can map the water levels, it will show you oftentimes which direction the water is moving. Well, since they're all the same, that data doesn't help us much. There is some evidence. Barker produced a water level map of pre-1975, before our pumping influenced the area so much. He showed that there is in the upper aquifer, there is a gradient of water showing that water is moving towards this, what I call the sink. So that was one piece of data that shows that information is correct. The geologic evidence is very strong throughout the Columbia River Plateau, not just in Moscow and Pullman. It's accepted sort of a base rule that water flows down the slope, down the dip of basalt contact. So the geological evidence is very strong. The water almost has to be moving towards this low area. Of course, what's it doing? It's this impervious ridge. It somehow is going around that nose, I call it, around those low areas and getting out in here to the Union Flat Creek area, connecting the two areas. There's no new data though to show how well that connection is. All we have is we can go up here to the north to Colfax, and we can go around, not shown on this map, we can go around to Genesee, south of the impervious ridge here. And those wells in the Grand Ronde show that their production is about only 1/3 of what we get in the Moscow Pullman area. So it's kind of inferred evidence that my thinking that this whole area, it's not just my thinking, but that this whole area could be uh, part of the barrier slowing down water movement. But we don't, I have to admit, we don't have that proof. So the model checked out pretty well, except it's too bad that we don't have some direct quantitative evidence. We have one piece. There is well number, Pullman number 8, Golder uh, uh, Enterprises ran a very detailed, complete major pump test on that well when it was completed. And I thought it was interesting that when they determined that after a certain period of pumping, that it hit a definite, hit a very strong boundary. About, I think they said 3,000 some feet from the center of of that well, a very definite boundary, and that was coincidentally about the same distance to the center of the anticline. So, but the problem is when you're doing a pump test like that, that boundary could be anywhere, but it didn't seem to me that that boundary could be in here in the central part of the basin where every well it's Grand Ron water, same water levels. So I think that's one piece of hydrological evidence that shows that there is a boundary there. The conclusion from all that work was that the water is coming across from Moscow and Pullman, these blue arrows. Let's just focus here in the Moscow Pullman Basin. This diagram's pretty complex. But the blue shows the water movement coming down from the Palouse Range and from Moscow. It moves into Moscow, moves across the basin, comes across, it hits these structures. Whether you believe in the structures or not, the water is then turned to the northwest because it's got to move down, dip, down slope. This is the structure here is the syncline. This black line is the anticline. So once again, the idea is the water's moving across, comes to Albion, forced towards Albion, it's forced to move to the northwest. The fact that there's structural control is pretty obvious. The more you look at it, and I found more references other than mine talking about the structural control. You got Snake River moving to the northwest. You got the uh, Union Flat Creek moving to the northwest. You got the South Fork of the Palouse moving to the northwest. This change from east-west to northwest, clearly structural control of the surface drainage. So I would say that there's structural control on the subsurface movement. One other thing I checked before leaving the west that I reviewed. Now, like I said, it's good to review your own work and other people's work. Never let a model sit still. One of the things that I talked about is that here's the South Fork. The South Fork of the Palouse is falling right along the the west flank of the anticline. And there's good information there from Moxley, WSU student, and from the Department of Ecology showing that there's influx on top of the Grand Ron contact, making this a potential recharge area. However, when I reread the articles, it doesn't, there's no proof there that that water's getting down into the lower aquifer. It's just definite influx there, opposite along Paradise Creek. Paradise Creek, Missouri Creek, these are not influxing streams. South Fork is, the reason it's influxing is because the stream is now on the contact at the base of the Wanapum, the basalt of Lolo. It's on the contact between the upper aquifer and lower aquifer. And so there is influx going in there. However, where's that influx going? After reevaluating things, I think the potential for it going into lower aquifer is not very significant because you come out here to the Flat Creek area, and by looking at some work by Hopster and by Heinemann, they both identify discharge into the Union Flat Creek drainages in the central part of that drainage. So I think this water we're seeing influxing up here is just discharging out here in the Union Flat Creek. One could say, well, it's because the erosion is down into the contacts out there also. That's true. But I don't think There's any strong evidence. It doesn't say there isn't any recharge to the lower aquifer, but I would say there's not much. Again, the talk today is focusing on recharge because that's where I made some adjustments. So let's take a little look. Here's what the original recharge model that I presented as sort of a summary of other people's work. You look at, here's the basalts ending, here's the low flow, here's the red units here showing the Grand Ronde basalts. The idea presented was that you're getting recharge from the east, getting down into these the slopes. This would be what I call the agricultural slopes on the Moscow Mountain. So I propose that's where most of the recharge is coming from, and getting down into the sediments and then moving to the west. Well, we'll recheck the data here, needed to make some adjustments. Turns out, I don't think this is the high recharge area. The only high recharge area is up into the mountains. So since recharge was so important, what I did, let's review somewhat the thinking on the recharge. And we're back only as far as 1995. We could go back to as far as 1925, where some ideas were presented about recharge, and lots of ideas and projects and reports since then. Let's just start a little bit about the thinking in more recent times. In 95, I presented this drawing. Some students, Andy Provant and Jack Pierce, had identified that the agricultural slopes, this will represent the agricultural slopes on the Palouse Range, were actually underlain by sediments and not granite. So the basement granite rocks are represented here. This would be up in the Twin Peaks area. This would be the agricultural slopes. So the model I presented was, I thought, well, the water is getting down into these sandy areas of those sediments and migrating out and percolating down into the top of the low, and that's where our recharge is coming from. Turns out I was correct about water moving across these channels. I think that's been verified by students of Aaron Brooks and data information presented to PBAC. However, Jerry Fairley from an extensive research report from drilling into the sediments down to the top of the Lolo, pointed out that he didn't think, or I wouldn't say didn't think, he strongly pointed out that there was just wasn't much recharge getting from those sands down into the Lolo flow. And we have research in Moscow which says there's water getting down into the top of the Lolo flow. Well, the whole point, whether I was obviously wrong on research, a lot of water getting into the top of the Lolo, it doesn't matter. The Lolo is not letting water down into the lower aquifers, down into the Vantage or down into the Grand Ronde through that basalt. Not significant amounts, but it wasn't correct that there was recharge coming through there. I think it was, I reinforced myself at the time. There was a nice study that I had overlooked, and I just want to mention it. Larson and others in 2000, based on our work at WSU, published a paper, and using isotope data primarily, she determined, and this was a sort of a lost article, I thought, at least I had overlooked it somewhat. She pointed out that there was shallow recharge was from the east. She just suggested that because she said it could be from precipitation, but there was, in her mind, or the people's mind, it was shallow recharge from the east. And what she meant by shallow recharge, when you look that up, when you looked up the shallow recharge, what she's talking about is the upper Grand Ronde, what we now call the R2. So she actually, I guess I should say, they nailed it. The water was coming from the east. But we sort of backed off of that since I was proving that my work wasn't totally accurate. We got into what I called the no recharge mantra. Earlier, Crosby, back in 1965, excuse me again, Crosby had pointed out, using determining some carbon-14 dates, that the Water was old, suggested the water in our basin was all Pleistocene. Douglas, 2004, 2007, very good analytical work, duplicated Crosby's information, pointing out that they're suggesting that we're getting all the water is old, we're not getting much recharge. Uh, Fairley, I mentioned his work. Uh, he focused on that funding was primarily from the state of Idaho. Drilled 40 holes through the sediments of Bowville down. I think 7 of those holes encountered the basaltic Lolo. Pointed out that there's not much recharge getting the Lolo. Uh, he also pointed out there's so much clay on the agricultural slopes that he doubted there was much recharge there. Another study supported by the state of Washington was Golden Associates, who looked at Kamiak Butte and some of the quartzite buttes as a possibility of recharge. Somewhat flawed study, excuse me, in the sense that because of poor land access, we did not get the access that we wanted. They only dug one exploration trench, and it showed too much clay, not much infiltration, and they concluded there was no recharge. All this together led a lot of people to think there's no recharge. It doesn't make any difference. We were drinking old water. That's all we got. Uh, we seem to overlook that. Led us into thinking this about no recharge. Let's look at what happened as we research extended on. I call them Jim Osinski's students. If you want to know the references, you need to go back and probably look at some of the earlier videos. But Jim Osinski from the University of Idaho had, funded by primarily from PBAC, students had been doing a lot of large-scale pump tests, starting way back actually in 2004. But the ones in 2009 through 2012, they were the ones that I think were the most significant. They all three recorded or did summarize that modern recharge was significant. This was shortly after the no recharge studies. And I don't think it changed people's thinking too much at the time. There were 3 theses, all came to the sort of the same conclusion. One of them was hired to do Moran was hired to do she was hired to do a consulting report for a PBAC. And she estimated that the recharge was 1 billion gallons a year. And what was significant about that number, if it was correct, it is an estimate, is that it was just a little bit less of what we were using, which I think was around 2.2, 2.3 billion gallons a year. So that is significant, even if the recharge is not enough to keep up with what we're using. It was a significant number. And interesting, shortly after that, let's see if I got the right one here. Oops. An independent study, not funded by PBAC, Pearsall and Sprinky, they had, using a whole different method, looking at water level changes related to earthquake wells and other methods, quantitative methods, they calculated there was significant recharge. They suggested that the recharge was approximately 2 billion gallons a year. They actually didn't present that number. What they said was that the recharge was about 90% of our drawdown. In other words, 90% of what we were using. So this is my calculation. If you take 90% about what we were using, roughly you come up with around 2 billion gallons a year. I just thought it was interesting that that was, in terms of big numbers, it was relatively close to the number that Moran had calculated. So all this work was showing that there was significant recharge. Hang on a second here. My thing is not working the way I'd like it to work, so we'll do it this way. So I started to look at some other work, reviewed Aaron Brooks and Jeff Langman, and I call them their students just because there's lots of publications here, and those names I think were given somewhat in some of the other earlier memos or earlier videos, excuse me. If you wanted to find out those names, you could contact Aaron in Soils Department, University of Idaho, or Jeff, the Geology Department, University of Idaho. Aaron actually started way back in 2004 and had noticed that there was recharge getting into the permeable soils on the Palouse Range. He then mentored several students from the Netherlands who determined the same thing, that there was modern recharge and that the recharge was significant along the slopes of the Palouse Range. So they determined it was modern recharge. And then Jeff Langman students, building on Aaron Brooks's work and working with Aaron Brooks, also determined it was modern recharge. And they added to another significant part was that they could trace snowmelt water in the system, the lower aquifer system in Moscow and Pullman, and that the water, that snowmelt water was coming from, of course, the Palouse Range, where we get the highest precipitation rates and the highest snowpack. Another significant thing they pointed out was that there was dead carbon in the system. Now, there are numerous ideas to how that dead carbon got there, but that may not even be all that important. What's important is there was dead carbon in the system. And this is where the earlier works went astray. The earlier calculations were not incorrect, but they made the assumption in the modeling that the aquifer systems was entirely basalt and therefore not any carbon in the system. So what Jeff's students, particularly Kyle Duckett, pointed out that when you recalculated with the dead carbon, that the numbers presented in the water system were too old. So this kind of, in my thinking, put the nails in the coffin. There's definitely water recharging from the east. That all checked out to what I presented. And remember, what I presented was that water was recharging from the east up here on the slopes, agricultural slopes, and from the mountain range. However, when I went over their works, I think I overlooked a couple things. Well, I did overlook a couple things. Let's take a look at what I looked at. So I reviewed Brooks and Langman again, and also went back and looked at Othberg and Breckenridge 2001. They had produced a official map. It's the ones you can see me behind here on the upper little photo. When you read Brooks in more detail than I had before, and I have to admit, I'm not the best quantitative person. You read Brooks closely and you realize what he was talking about was the recharge wasn't occurring on the agricultural slopes. The recharge was occurring up in the forested areas. In fact, he agreed with Fairley, the fact that there was too much clay. There wasn't, their experiment showed that there was not much recharge getting down on the slopes. It was coming from the forested areas. And of course, that laid nicely onto Langman's work, which says a lot of our water, most of the water we're drinking is coming from snowmelt water, and it can be traced from the mountainous areas all the way to Moscow and Pullman. When I relooked at Othberg and Breckenridge, this was a little bit embarrassed. This is good geological work. I knew both of them. When you look at their maps, found another piece of evidence or another line of evidence showing that Brooks and Langman were right. Let's take a little look at their map. Here we have Twin Peaks over here on the right of the diagram. This is US 95 over here on the left. This is a copy, an extract from their map. Okay, so you see the ridge here. This is the ridge of the Palouse Range, and it shows all these yellow and brown patterns. And then you have the forested area here in this yellow pattern. And then you have the slopes down here with the red over the top of what's called the slopes. This is the agricultural slopes. This is the forested areas, and this is the very, very top. The red dot things here is the end of the loess. The loess is thinned out. So let's take a look at what they were talking about. When you look at the description of this material, you realize he's talking about conglomeratic layers, permeable soils, weathered granite, all across the ridge. When you look at the forested areas, some of the same conglomeratic units, permeable soils. Permeable soils identified also by Brooks in 2004 and his students much later. So get to thinking, well, this is where the precipitation or measured precipitation is coming from. So the geologic data here is laying right on top of the soils information from Brooks' students, from the geochemical data from Langman students. So this is the area of where most of our water is coming from. When I think back, how did I miss that? How did my students miss that? Well, when you go across that area, what's interesting is a composite of many landowners, public land, is part of it's being logged, part of it's excellent trails. What I noticed when I went across there and didn't think about, I was always interested in the rocks. You have to look pretty hard to find the granite outcrops. The bedrock is not close to the surface. This area, even though you can find outcrops and you go, it's all granite, mark that on my map. Most of the area is underlain by a thick mantle, soils, conglomerates, weathered granite. That mantle is where the water is infiltrating, not down here on the slope. So we need to correct the model a little bit, make an adjustment. If you're using my diagram or using this diagram, mark out the recharge here, move the recharge up into the mountain fronts. That's where the water is coming from. And this diagram doesn't help you here a little bit because it's got to get down off of the mountain, off of that mantle of material, and then get into the sediments of Bowlville, and then move down in towards into Moscow and across the basin to Pullman. But the diagram needs to be adjusted a little bit, and your thinking needs to be adjusted a little bit. So that's where, in my mind, there's no doubt that's where most of our water is coming from. And that leads to the conclusion I've been teasing you with a couple of times. The simple conclusion is if we look back across at the first line, the water is not infiltrating our ground round water, our lower aquifer water is not significantly being supplied by any kind of surface precipitation, by any kind of influx into the stream. It's not coming from the slopes. It's not being infiltrated on the agricultural slopes of the mountains, as I had earlier suggested, and other people have suggested. It's coming from the forested areas. This is where your water that you're drinking and that you're using is coming from. And it's interesting, we don't pay sometimes enough attention to just logic. Like it's logical to why do we have so much water? There has to be some sort of barrier keeping the water in our basin. Well, if you're standing down there, I'm going to tell you a story of a farmer way back 50 years ago when I was then working at WSU. Went out with this farmer to meet, looking, locating a well right here on the edge of Kamiak Butte. And we moved him away from the quartzites, moved the driller into where there were basalt. So we got to talking about where does this water come from? And of course, that was 50 years ago. Talked a lot about infiltration through the loess. There have been experiments showing that you could get 3 or 4 inches through the loess. That data has been considered not accurate. But I remember that farmer. I was only in my 20s. I thought he was, ancient. Maybe he was 60 or 70. He'd worked here all his life. And what he said was, I've dug a lot of holes in that loess. I've plowed a lot of that loess. I've had holes drilled in that loess. I've dug holes in the spring. I've dug holes in the fall. I've dug holes in the winter. The water ain't getting through that loess. Doesn't matter. It's not getting down through there. Up there is where the water is coming from. Up there on the mountains, that's where the water is, and that's how it's getting down into our system. Well, I agree with that. I think the evidence is extremely strong Most of the water you're drinking and using in the Moscow Pullman area is coming from those forest areas. And that leads me to a suggestion, which you can take it or leave it. I realize that it's very important to look into the future to where are we going to access additional water since we have a certain amount of recharge and we are using more than is being recharged. But I also have a suggestion to that. That's important to look ahead and important to look at alternative resources. But let's don't forget our watershed. And we have lots of experts in the area uh, that are at both U of I and Washington State University and several groups that are experts on surface hydrology, uh, forest hydrology, forest ecology. Uh, Lots of people that use what I call the Moscow Mountain area, it's really the southern Post Range. We should be looking at protecting that watershed. It's the water we have. It's the water that we're going to use in the future. It's still going to make up a major portion of the water that you need. So just a thought, protect your watershed. Don't forget research. Don't forget keeping the research going. It's year after year research is important. Right at the moment, Jeff Langman has been suggesting some uh, research. All that research needs to be continued. You can't do it all at once. Keep the research going, protect your watershed. And I'd like to thank PBAC particularly for allowing me through the years to present my information, to provide some support at times uh, for the research and for putting my talks and on their webpage. Thank you very much.